suppose that you are interested in physics because you are electrical engineers. You must have some affiliation to science. Now this is the hard part. Start record here also. This was the lecture. And here. This is the practice. So, here, first of all, sorry, last time I made a mistake. At the very beginning here, this minus 34 was multiplied by 15, and I got minus 17 instead of minus 19. That's why finally I had an order of magnitude difference. But still, until I was here, I found the mistake and corrected it. Okay, so here we have exercises. Yeah, I know. Yeah. Okay, the electron has a kinetic energy, blah blah blah. What is the wavelength of the associated de Broglie wave? Because you haven't heard about de Broglie waves, we cannot do this exercise. Last time I did this exercise, the second one, and now the third, fourth, and fifth one are coming. Whoa, we will see. Ideal world, I would be prepared and just beam the results, but it's not that one. Okay. 3. A photon ejects an electron with a maximum kinetic energy of 0.54 electrovolt from a metal for which the work function is 3.74 electrovolt. What is the energy of the photons in electrovolts? Great. What is the wavelength of the applied ultraviolet radiation? Here. I need some help for myself. again. Okay, so exercise. We have the method. First, you have to draw all this down. So, we have a photon. This is the photoelectric effect. We have a photon, it hits an electron that is close to the surface of the material, so it could leave it. The photon is here, and it hits the electron. So the kinetic energy is this electrovolt. Apologize. This electrovolt. Does it say anything to you? To me, because I'm dealing with the particles, yes, it's energy. Volt, charge, gives something in joule. Just this electrovolt is so small that we can use it. It's more appropriate. But this is like joule, this is energy. Have you ever heard the electrovolt before? Sorry. Last time you should have told me, because I forgot it. It's natural to me, because I work with it. These are electrovolts. In the magnetosphere of the Earth, the particles reaches kiloelectrovolts, sometimes megaelectrovolts. The flashes on the sun, and also the cosmic rays could have gigaelectrovolts. The big hadron collider in CERN in Switzerland could have teraelectrovolts. It's energy, nothing more. So if you calculate, you multiply volt and the charge of the electron, you got something in joule. Okay? Sorry. Always tell me, even at lecture, if you do not understand anything. It's not a shame. I always tell my students, I was not born with this knowledge. It came from a classmate when I was a university student. He said this in a more common way, with interesting Hungarian words that you don't want to learn. So, I also had to learn this. And because of me, I remember usually how I understood these things. And it's not easy. And it's not easy if you're at university and you learn something from mathematics, and it should be in the syllabus, but it isn't. I don't know what background you have, for example. Many Hungarian students now have very mixed background. It was very typical that the level of the education was proportional to the size of the city where you grown up. So the best schools are here in Budapest, and large cities are also good. So just tell me if you don't understand that. You don't do something. So you have the photon, it hits one electron, that's a quantum effect. It gave a Nobel Prize to Einstein. Not for the general relativity theory he got the Nobel Prize, he got for this. And the energy, the kinetic energy, is this small. Not so small, because the work function was that one. I will explain you what is in the metal later, a few lectures later, a few weeks later. So it's bonded, the electrons are bonded by the ions of the metallic atoms. It's a crystal actually, and the nodes are the atoms, and the electrons are a common cloud. That's the metal. That's why the metals are very good in leading the current. But these electrons are bound. There is a negative potential which keeps them in the metal, otherwise just they would throw down and we would have a crystal with positive ions. So they are bound. And that bond is this 3.74 electron. I like this. No iPad, just bubbles. Great. Okay, so the first question. How much was the energy of the photon? The second, what is the wavelength of the applied ultraviolet radiation? It helps. That's why you have to read always. Ultraviolet means the wavelength must be shorter than 400 nanometer and longer than 0.1 nanometer, but you should know only this 400. I know the other because I work with it. Okay, the first part is simple. So, we had an electron, we know its energy, we know this work that must be made to remove this energy. So the energy of the photon became the kinetic energy of the escape electron, and also we have this work. Nothing more than I'm right? I think yes. So this is the answer for the first question. Usually then you have to underline twice and write a test. It's the same. This was easy. The other part, what is the wavelength of this radiation? Doesn't matter. This was the A. B is quite simple. Also, the E photon is the Planck constant times the frequency. Well, usually I write mu, but for you I write F. And that's Planck constant C per lambda. Okay, you have learned mechanics, didn't you? You know that the multiplication of the wavelength and the frequency gives the propagation speed of the wave. You know it. Great. Because here okay? You know this. This is the same for electromagnetic waves. Let's wave. Okay, then what I have this manicure. So okay, we are close. How much is the blunt stuff? 6.16, how much? 6.62 times 10 minus how much? 32.
Yeah, minus.
32? Not 34?
Yeah, 34.
34, okay. And the unit? Joule second, isn't it?
Yeah.
It's important.
Joules.
Ah. Okay. And we have the speed of light. We have this in electrons. That is very nice. Just not good here. So this is over. So this is okay. Just I need this in joule. So this is how many? 1.6. And what is the exponent?
Minus
19. 19. 2.9.
Where?
Sorry?
Uh, 6.8.
It's better. Six point eight and
6.848.
what is the next digit?
4 and 8.
8 and
8, 4, 8.
4, 8. Okay, it's then it's 5.
Yeah.
No,
Okay.
doesn't matter. Okay, and then that's okay. Okay, I will need this here. And this is in Joule. That's great. And now I will need help. So it's minus 17 times 8, then it's minus 9 meter. That's fine. Just I need someone to multiply the small number. So 6.62 times 3 divided by 6.85.
It's 7.
2.8 to the power of minus 7.
2.8
2.8
and
to the power of minus 7. Power minus 7. Minus 7.
Wait a minute. So what is the 2? Wait. Something. Yes. Usually I don't sleep so much before this class, and you are right. Absolutely. This is minus 7, and this is you got 8, and how much?
9.
9. That's 9. Well. Okay, then only for you. The nanometer is not SC, but I'm familiar with nanometer and not meter of the wavelength. So this is the wavelength of that photon. It's okay? Understandable? It's quite simple. So there are two things that you need. The photoelectric phenomena, and also this Planck energy of the photon. This is the new knowledge. The other is from primary school. Most of us. It's okay? Can I continue?
Yeah.
Great. Oh. Very well, this bucket or water there. Doesn't matter. No. Next. Oh, wait. I forgot. Because we can check this. This is okay? Then it means that's okay? Or almost. Yeah. We are good. Just I forgot that we can check this. Okay, Compton. Compton scattering. In a Compton scattering experiment, X-rays with a wavelength of 0.124 nanometers are used. It is the electron mass is given. Question A, at what scattering angle does the wavelength of the radiation increase 1%? Question B, at what angle does the wavelength become 0.5 larger? Okay, so this board is full, but I have other. Magic. I don't know whether it's a good idea or not, because then. But I will write down the stuff. Oh. Not easy. Here. Okay. So, we have a photon, gamma photon, and it impacts with an electron. I talked about positron. Compton during the lecture. The Compton scattering works on positron too. Just the result is there is a easy way to create positrons. In radioactivity, the beta type of radioactivity is there is negative and positive. Negative gives electron, positive gives positron, but it's rarer. Doesn't matter. Rare. So I have here a modified photon, and the electron goes in this way. So the question is the So this is the Compton scattering. Okay. It has 0 null wavelength. And it says, I'm lambda null, not 0 null, sorry. also gives the electron mass. Question A. So what angle that give one person longer wavelength and the B I don't know. Delta. Rectangle. This is the 0.05% more, and this is the 1% more. Okay, so we have the task. What is the task? What is this quantum scattering? We have electrons bounded in an atom. We have high energy photons called gamma ray radiation. One photon hits the electron and gives energy. Some part of the energy is given to the electron, so the electron leaves, and this energy changes the energy of the gamma photon, what means it changes its frequency or its wavelength in this case. If the frequency, if the wavelength is higher, then the energy is lower. Wait. Yes. And when the frequency is higher, then the how can I say it? The frequency is wait. Larger wavelength means lower energy, so larger frequency means higher energy. Okay, so we have this quantum scattering. And we have nodes. The nodes says the lambda change is given by this formula, where h is the Planck constant, m null here is the electron, c is the speed of light, and then here that's cos gamma. What we have? We have this lambda, and therefore we know the delta lambda, it's 1%. And what is the question? Yeah, the angle. Okay, so okay, I hope I didn't make a mistake. Now we have something for this one. So this is 1 minus was it 6.62 times 34? Please help me. This is the, that's it, great. And we missed something. Here is the wavelength, and we need 1%. That means 0, then 10. I hope I'm right. And this is nanometer. That's bad. Three. I'm right? Yes? Okay, so it's okay. Quite okay. This is joules kilogram times meter cubic and per second cubic, so it no cubic square. So the dimensions are fine, and the result will be dimensionless. There won't be any dimension, and that will be 1 minus 9 what 1 times 3 per 6 2 sorry 1 okay times what is it? Okay, so this is plus 3 plus 11 minus 12, so it's minus 1. So please tell me what is this. Yes?
Why is the wavelength smaller than the wavelength we have from the exercise? Like the wavelength they gave us is 0.124 nanometers.
This is the delta wavelength, so the change of the wavelength.
Yeah.
Yes.
I know that it's different, but how can we conclude that?
Sorry?
How can we conclude that?
Okay, so the question is 1 point. The wavelength should be changed 1%.
Oh, okay.
I hope I did the multiplication right. So could you please tell me what is the result of this? Any of you?
The power of 10. How much the power of 10?
It's minus 1. Just please calculate this 9.1 times 3 per 6 per 6 multiplies 1.24.
Its solution is 0.5.
0.5? Really?
Solution.
The full solution.
Yeah.
Okay, so this is 0.5, then it should be also 0.5. So.
Also.
Okay. Doesn't matter. So you calculated this. Where is this? Okay, so it means it's quite a large stuff. Of course, you can calculate the angle if you want in radian or angles or something like this. So class ends at 3, isn't it? Okay, so the B is very simple. You do the same homework as just this number will be this multiplied 0.05, and the angle will be different. Is it okay? Okay. Let me check something. First of all, okay, so what is the solution of this? Okay, you were not perfectly accurate, but that's fine. The angle is quite large, so it's 60. I thought this is it. So we had a good stuff, I mean good cooperation. And what I would like to check is this. The exercise 5 is the same like this one. You have to use the same effects. Only one thing, the energy of the proton is calculable from the change of the wavelength. You need Planck constant multiplied the c, the speed of light, and divided by the wavelength. But be careful, there are two wavelengths. So you cannot just divide the delta. Okay, so officially the class is dismissed and it's over. I think one lesson is not so much. I had mathematics course last semester at the University of Page. And we had two lectures, 2 hours lectures and 2 hours practice. Is it enough for you? Could you follow? Is it okay?
Yeah.
Okay, that means that I can give you. Oh no. Okay. Next time we have to fix the first because we haven't heard about the radial waves, and then I can give you homework. I'm official on what you should say. Okay, thank you very much. Have a nice day. See you next time.